In this series of lectures, we introduce some basic and important concepts in calculus. As an entry-level course, we often adopt approaches that are intuitively clear but might not be mathematically rigorous. In particular, we will not use the famous epsilon delta language. In this lecture, we will see how to use second derivatives of function to find its local maximum or minimum points. All right, first let's recall the following theorem or the following conclusion we proved in a previous lecture. It says this. Okay, so suppose our function f, which we know it is twice differentiable. This is x and this one. Right, so the function is defined from a to b. This is a and this is b. Okay, let's look at one first. Okay. All right, so it says if the function has a critical point, has a critical number at x0, so that's where the derivative of the point equals 0. If the function is, if the second derivative is positive, so this means the function, this we know, this implies the function is concave up, then we'll have the function has to be like this. Right? Okay, so this implies the function attains absolute minimum at the point x0, right? In other words, we have the fx is always greater than f0 whenever x is not x0. Similarly, if we know the second derivative is less than 0, right? So if we know the second derivative less than 0, and this we know the function is concave down, right? It's concave down. Now for this case, then what we have is, okay, I have this is the function, this is x and this is y, right? So this is the a and this is the b. Again, I will point, this is a critical number, so this one is equal to 0. Okay, now this time the function is concave down, right? So the function is concave down. Let's see right here, the function is concave down. And then it's clear what we have is the function attains an absolute maximum at this point. So in other words, all the values of the function is less than the value at this point whenever x is not the same as x0. Okay, now this will give us the so-called second derivative test. Now the test says this: suppose our function that is continuous and also is twice differentiable on the interval, right? So here we have a function. Let's say this is my interval. Okay, suppose this is the whole interval, which is from a to b. This is the whole interval, which is from a to b, right? Okay, so this is the whole place where the function is defined, right? So, okay, let's put this, put that. Okay, all right. What do we know is the point x0. So again, we have the critical number. Have a critical number. Okay, let's look at the case one. The case one says, I know the derivative at the point x0 is positive. So I know the second derivative of this one is positive, right? The first derivative is 0, okay? All right, now the point is, because I have the function is, you see, I have the function is continuous, right? So if the second derivative is positive at this point, this implies the second derivative is positive, right? This one will be positive for x is near, right? So for x is near the point x0. So let's say, okay, so suppose we have this place somewhere is near it. Okay, so for example, we can put CD. So right here, I get, okay, within here, I have this x is positive, right? Only within this range. In general, it's not in the whole place. But anyway, okay, so then I end up with a situation. If I look at this CD, I'll have the second derivative is positive, and it is 0 at one point, right? The first at one point. Then you see, this is basically the situation here, right? So I have the second derivative is positive, then it's a critical number, and this implies this one will be a minimum. Okay, so then this implies x0 is a minimum. But minimum is not in the whole range, but they just in this sub-interval, say CD. So that's what we call is local. So that's why it's local. We cannot guarantee so it might not be. So here we have to be careful. This is local. So it's a minimum only on the subinterval. So not necessary. Okay, so this is important, keep in mind. Not necessary. Sorry, the absolute minimum in the whole interval AB, right? Only in a subinterval. So that's why we call it's local. It's a local minimum. And similarly, for the other guy, if I know the second derivative of this one is less than 0, right? The first is 0, and then because it's continuous, so I get the second derivative. So this will be less than 0 for the x is near this x0, right? Okay, so we say, all right, so I have, let's say C and D, so this nearest them right here. In this range, I'll get this second derivative less than 0. Okay, so then combined with this is 0, we know, okay, then we have this situation, right? So if the function, you have a critical number, and then the graph, the second derivative less than 0 is concave down, so then you get a maximum point, right? You get a maximum point. Okay, now within this range, so from here I combine together. I say, okay, so I get x is maximum point. Now in this sub-range, right? In this interval CD, but it's might not be in the whole range. But again, so here we want to emphasize, not, okay, so not necessarily the absolute maximum in the entire interval AB. So that's why what we get again, here we get is local. And here also, again, is local. All right, okay. All right, so this is the second derivative has, keep in mind, it helps us find its local maximum or minimum point. It's local, not necessarily the absolute maximum in the whole domain, right? It's just local. All right, then conversely, we'll have this. If you say, okay, suppose I have a local maximum minimum at the point x0, then of course, by Fermat's theorem, Fermat theorem tells us if I have local maximum minimum, then it has to be a critical point, right? So this by Fermat theorem, and then also we get this one has to be non-negative. So here, the starting point is we have is big or equivalent to 0. The answer is, you say, okay, why that's true? Why it has to be like that? The thing is, like, if not, then you must have this one will be like here, right? If it's not non-negative, you just get this one will be less than 0. But then by the test, right? So by the test implies x0 will be a local maximum, which is impossible because we already know is a local minimum, right? Okay, so similarly, if I know the function has a local maximum, then again by Fermat theorem, it has to be a critical point. And then by the test, we know this one has to be less than 0. You say, okay, you say why? If not, then I get the second derivative will be having positive. Right? If it's not non-positive, it has to be positive. And then this by the test, right? So test says, okay, if it's positive, that means x0 is a local minimum, but which is impossible because we already know it's a local maximum. All right, so that's the converse. Now then you say, okay, why do we need to add the equal sign here? That's because you can have things like this. You say, okay, I can have things like this, right? So I have, you see, there are situations. You see, suppose you see I have the function. This is the function, right? It's y equals to x to the 4, right? X equals to the 4. Maybe let me put it here. Okay, so if I look at the function, this is y to the x to the 4. And you know, this one is not only local minimum, but this is absolute minimum, right? So this is the minimum point when x equals 0. But if you take the second derivative of this, you get 12x squared, right? And which is 0. So this one is 0 when x equals 0. So that's why if you look at the converse, you have to put the equal sign. But anyway, the general test says if you one direction is if you have this one positive, then you get this local minimum. If it's negative, then you get this local maximum, right? Get a maximum. Okay. All right, now let's use that to find local maximum or minimum of the function. Okay, so here we have a proof. So here I have this is fx equals x squared and x minus 1. Let's find the first derivative. Okay, so this we write out is x cubed minus x squared, right? So if I look at the first derivative, it will be 3x minus x. Okay, so this will be just x, 3x minus 2, right? 3x minus 2. Okay, then if I look at the second derivative of this, it will be 6x minus 2, okay? All right, so then I have, first of all, you find the critical point, right? Find the critical number. This one equals 0 if x is 0 or x equals to 2/3, right? So we have two critical numbers, okay? Then if I plug this critical number into here, right? If I have the second derivative of 0, this one will be -2. This is less than 0, right? So, okay, this is less than 0, so implies it's a local maximum. So, okay, it's a local maximum. And then if I evaluate at 2/3, this will be 4 minus 2, which is 2, which is bigger than 0. Okay, so this is bigger than 0, right? So, okay, this is bigger than 0, so implies it's a local minimum by the test, right? By the test. All right. Let's try to draw the picture. So here we find, let's try to draw the picture. So here we find all those local maximum minimum, right? So this will be, this guy, 0 is local maximum, and 2/3 will be a local minimum. Let's try to draw the graph. Right? Let's see more information about this. We have, so first of all, we have the fx is bigger than 0 if x is bigger than 1, and fx is less than 0 when x is less than 1, and the fx equals 0 if x equals 0 or 1, right? Okay, and let's look at the concavity. From here, I know this one is bigger than 0 if x is bigger than 1/3. This is less than 0 when x is less than 1/3, right? Less than 1/3. Okay, that means this will be concave up, and this is concave down, right? So this will be concave down. Okay, let's draw the picture. Let's use those information, try to draw the picture. And then you see what we have. All right, okay, that's what we have. So I have it's 0, this is local maximum. And then I have this is 1, right? Okay, so this will be the 1. Okay, so that's the graph. That's the graph what we have. This is the 1. The point of refraction is right here. So this is, here is what we have is 2/3. The 2/3 is the place where we have this is local minimum, right? It's local minimum. So this is the point which is 2/3, and the graph changes the direction, changes the concavities right here, right? It's a point, so this will be 1/3. Okay, so the graph is concave up, it's 1/3, right? So it's okay. So this is concave up, and then it is concave down, right? It's concave down, so it's like that. Okay, all right, and that's what we have. So this is x, this is y, and this is 0. Okay, part is concave up. This part is concave down, and then we have this is local. This is local minimum. This is local maximum, and then here we have this local minimum. The point of refraction. So if we want to inflection point, will be x equals 1/3, right? So x equals 1/3, and then the y will be y equals to 1/3 squared times 2/3. So that's what we have, right? So it's 27 and 2. Okay, so that's the point. Negative. Okay, so negative, right? Just negative. Okay, so -2/27, and this is the point of inflection.